The natural way to describe the position of any point is to use Cartesian coordinates. In 2 dimensions, it's quite easy. We just have a picture like this, and so we have an x-axis and a y-axis. An origin O where they cross. And if we want to have vectors in that arrangement, what we would have is a vector I associated with the x-axis and a vector j associated with the y-axis. What are these vectors I and j? Well, they have to be unit vectors. A unit vector I and a unit vector j. In order to make sure that we do know that they are unit vectors, we can put a little hat on the top. So, if we have a point P, and let's say the coordinates of that point are 3, 4, then the position vector of P, which remember is that line segment joining O to P, is 3I plus 4j. Notice the crucial difference. That's a set of coordinates which refers to the point. That's the vector which refers to the position vector. So point and position vector are not the same thing. We can write this as a column vector, 3, 4. And sometimes this is used, sometimes that one is used. Just depends. What about moving then into 3 dimensions? We've got x, y, and of course the tradition is to use z. So let's have a look. Let's draw in our 3 axes. So there we've got x, y, and z. I'll always write z with a bar through it. That's so it doesn't get mixed up with 2. I don't want the letter z being confused with the number 2. So I've got these 3 axes, all at right angles to each other and meeting at this origin O. And of course I'm going to describe any point P by 3 coordinates, x, y, and z. Now when I drew up this set of axes, I indicated them quite easily. I could, of course, interchange x and y. I might choose to interchange y and z. But this is the standard way. Why is it the standard way? What is it about this that makes it the standard way? It's standard because it's what we call a right-hand system. Now, how can we describe, work out what is a right-hand system? Take your right hand and hold it like this. Middle finger, forefinger, and thumb at right angles. This is the x-axis, the middle finger. This is the y-axis, the thumb. Now, rotate as though we were turning in a right-handed screw. And we rotate like that. And so the direction in which we're moving, this direction, becomes the z-axis. So we rotate from x to y, and we move in the direction of the z-axis. So it's right-handed rotation as though screwing in a screw right-handedly. Notice that it works whatever axis we choose. So if we take this to be y, again, the thumb, and we take this to be z, then if we make a right-handed rotation from y round to z, we will move along the x-axis. So let's do that. We can see that as we rotate it, we are moving right-handedly along the x-axis. And you can try the same for yourself in terms of rotating from x to z and moving along the y-axis. So, that's our right-handed system. So let's have a look at that in terms of having a point P that's got its three coordinates, x, y, and z. So we have x and y and z, and our origin O. We'll take a point P anywhere there in space. And what we're interested in is this point P. It's got coordinates x, y, and z, and its position vector is that line segment OP. And so we can write down OP bar is equal to xi plus yj plus z, and the unit vector that is in the direction of the z-axis is taken to be k. So again, notice the difference. These are the coordinates x, y, z. This is the position vector. Coordinates and position vector are different. Coordinates signify a point. Position vector signifies a line segment. We sometimes write, again, as we did with 2 dimensions, we sometimes write this as a column vector, x, y, z. Now, there are various things we would like to know and certain notation that we want to introduce. For a start, what's the magnitude of OP bar? What's the length of OP? Well, let's drop a perpendicular down into the xy plane there. And then let's join this up to the axes there and across there. Now, let's just think what this means. This length here is the distance of the point above the xy plane. So it must be of length z. This length here and here is the same length. It's the distance along the x coordinate. So that must be x. And that's also x. Similarly, this is y, and so that must be y as well. So if we join up from here out to here, what we have here is a right-angled triangle. And of course we've got a right-angled triangle here as well. So this length here, if there's our right angle, this length using Pythagoras must be the square root of x squared plus y squared. And so because we've got a right angle here, if we use Pythagoras in this triangle, then we end up with the fact that OP, the modulus of OP bar, is the square root of, we've got to square that and add it to the square of that, so that's just x squared plus y squared plus z squared. Now, I'm going to draw this diagram again, but I'm going to try and miss out some of the extra lines that we've added. So, x and y and z. We'll take our point P with position vector OP bar. Again, drop that perpendicular down onto the xy plane. And I'll draw this in across here and that in there. Now, this line OP makes an angle with this axis here. It makes an angle alpha. And if I draw it out so that we can see it, let me call this A. If we draw out the triangle so that we can actually see what we've got, then we've got the line from O to A, there, O to A, and we've got this line going out here from A to P. And that's going to be at right angles there, like that. And so if we now join P to O, we can see the angle here, alpha. Now we know the length of this line. We know that it is the square root of x squared plus y squared plus z squared. And we also know the length of this line. It's x. And that is a right angle. And so therefore we can write down cos of alpha is equal to x over the square root of x squared plus y squared plus z squared. Why have we chosen this? Well, cos alpha is what is known as a direction cosine, because it is the cosine of an angle that in some way helps to specify the direction of P. And alpha is the angle that OP makes with the x-axis. So of course what we can do for the x-axis, we can do for the y-axis and for the z-axis. So we have cos alpha, which will be x over the square root of x squared plus y squared plus z squared. Cos beta, which will be the angle that OP makes with the y-axis, and so it will be y over the square root of x squared plus y squared plus z squared. And cos gamma, gamma is the angle that OP makes with the z-axis, and so it will be z over the square root of x squared plus y squared plus z squared. So these are our direction cosines. These are expressions for being able to calculate them. But there is something that we can notice about them. What happens if we square them and add them? So what do we get if we take cos squared alpha plus cos squared beta plus cos squared gamma? So let's just calculate this expression. Cos squared alpha is going to be x squared over x squared plus y squared plus z squared. Cos squared beta is going to be y squared over x squared plus y squared plus z squared. And cos squared gamma is going to be z squared over x squared plus y squared plus z squared. Now we're looking at adding all of these three expressions together. Cos squared alpha plus cos squared beta plus cos squared gamma. Well, they've all got exactly the same denominator, x squared plus y squared plus z squared. So we can just add together x squared plus y squared plus z squared in the numerator. So that's x squared plus y squared plus z squared all over x squared plus y squared plus z squared. Of course, that's just 1. So the squares of the direction cosines added together give us 1. What possible use could that be to us? Well, one of the things it does mean is that we have the vector, let's say, cos alpha I plus cos beta j plus cos gamma k. That vector is a unit vector. It's a unit vector because if we calculate its magnitude, that's cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. Take the square root, that's 1. So this is a unit vector. Further, this is x over x squared plus y squared plus z squared, y over x squared plus y squared plus z squared, and z over x squared plus y squared plus z squared. And so it's in the same direction as our original OP, our original position vector OP bar. And that means that this is a unit vector in the direction of OP bar. And that may prove to be quite useful later on when we want to look at unit vectors in particular directions. For now, let's just have a look at doing a little bit of calculation. Let's say we've got a point that has coordinates 1, 0, 2, and a point that has coordinates 2, minus 1, 4. The question that we might ask is, if we form the vector AB, what's the magnitude of AB and what are its direction cosines? Well, let's just have a look at this. Let's remember that OA bar is I, no j's, and 2 k's. That OB bar will be 2i minus 1j plus 4k. We want to know what's the magnitude of the vector AB bar. Let's just draw a quick picture just to remind ourselves of how to get there. There's A and its position vector with respect to O, and there's B with its position vector with respect to O. And if we're wanting AB, that's from there to there, and so we can see that by going from A to B, we can go round AO plus OB. And so therefore that is OB bar minus OA bar. So that's what we need to do here. AB bar must be OB bar minus OA bar. And all we do to do the subtraction is what you would do naturally, which is to subtract the respective bits. So it's 2i take away I, that's just an I bar, minus j take away no j's, so that's minus j bar, and 4k take away 2k, that's plus 2k. So now we have our vector AB bar. We can calculate its magnitude. AB modulus of AB bar, that's just AB, the length from A to B, and that's the square root of 1 squared plus minus 1 squared plus 2 squared. And altogether, that's 1 plus 4, square root of 6. And the direction cosines are cos alpha, that's the x-coordinate over the modulus, so that's 1 over root 6. Cos beta, that's minus 1 over root 6, the y-coordinate over the modulus. And cos gamma, the z-coordinate over the modulus. Now, this is a fairly standard calculation, the sort of calculation that it will be expected you'll be able to do and simply be able to work your way through it very quickly, very, very easily. So you have to be able to practice some of these, you have to be able to work with it very rapidly, very, very easily. But always keep this diagram in mind, that to get from A to B to form the vector AB bar, you go AO bar plus OB bar. And so that's the result. So to form AB, it's OB bar, take away OA bar.